Now we're going to consider z as a function of x and y, where both x and y are functions of s and t. In the previous video, I used a tree diagram, and I just took for granted that we're going to use a tree diagram. I should say the tree diagram is really useful in keeping track of all of the derivatives and partial derivatives. Here at the top of the tree diagram, we're going to put z. And since z depends on both x and y, we're going to branch off z. So we have x and then y. Since x depends on both s and t, for x we're branching underneath it, right, with s and then t. Likewise for y. We're going to branch y and we have s and t. The idea here is that we're going to consider all the possible paths, right? So z depends on x, depends on s. Z depends on x, depends on t, right? Even though x depends on s and t together, right? And then likewise, z depends on y, depends on s. Z depends on y, depends on t. We're going to do some multiplying and adding as we did before. Let's first talk about the branch that starts in z, goes through x, and then ends with s. To talk about the derivative of z with respect to x, because z depends on both x and y, you see it branches here, that would be a partial derivative of z with respect to x. When we talk about the derivative of x with respect to s, because it branches underneath x, x has more than one input variable, it will also be a partial, this time the partial of x with respect to s. Now I'm not going to have enough room to write that down for everything, but I'll say that because, again, x branches, right, depends on both s and t, when we consider the derivative of x with respect to t, that's also going to be a partial. And likewise, when we talk about z with respect to y, it's a partial, and y with respect to x, it's a partial. And finally, again, z with respect to y is partial. I'm not going to write it again. Y with respect to t is a partial. And I'm being a little bit economical in my speech. The partial derivative, right, is how I should say it out loud. So then the question becomes, well, how many derivatives are there of z? And I want you to just kind of pause for a moment, not pause the video, just think for a moment the answer to that question. If you want to pause it, go ahead. Z has a derivative with respect to s, the input variable, and z has a derivative with respect to t, the other input variable. And so z has two derivatives. Because we have two input variables, s and t, they're both partial derivatives. The first two partial derivatives of z are partial of z with respect to s is equal to, now for this what we need to do is we need to follow all the branches that end with s, right? All the ones that start with z and end with s. So the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. And I'd like you to just quickly pause the video. I'm not going to do the graphic that says pause here, but pause the video here and write down the partial of z with respect to t. You should have paused it. You should have said the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. All right, so maybe you did pause it. You know what? I'm sure you did pause it. Great. Cool. Thank you for playing along. So the bottom line here is in figuring out whether it's a partial or an actual derivative with Latin d. The thing I'm taking the derivative of, and here it's z at the top, right? Does it branch? If it branches, it's a partial. At x, if it branches, it's a partial. And then we have to consider ultimately how many input variables are in the very, very bottom level. If it's only one, then we can talk about the derivative of z with respect to that variable. If it's more than one, then you're going to have that many partial derivatives with respect to s, with respect to t in this case. Now let's suppose that z is equal to the inverse tangent of x squared plus y squared. X is equal to s times the natural log of t. Y is equal to te to the s. I would like for you to pause the video and find the partial of z with respect to s and the partial of z with respect to t. Now you'll notice I'm using colors in a different way now. We have the partial of z with respect to x is equal to 2x divided by 1 plus the quantity of x squared plus y squared squared. That denominator there being the derivative of the inverse tangent function, right? And then 2x in the numerator because of the chain rule. Then the partial of z with respect to y, pretty much the same thing, but 2y in the numerator divided by 1 plus the quantity of x squared plus y squared squared. And then the partial of x with respect to s is natural log of t. The partial of x with respect to t is s over t. The partial of y with respect to s is te to the s. Partial of y with respect to t is just e to the s. And then what the colors are indicating is that we need the partial of z with respect to s. And so for that, we need partials with respect to x and y, but then ultimately we need their partials with respect to s. And so we end up with a product. And then, well, actually it's a sum of two products, isn't it? Partial of z with respect to x is 2x over 1 plus the quantity of x squared plus y squared squared times the natural log of t plus 2y over 1 plus the quantity of x squared plus y squared squared times te to the s. And then the partial of z with respect to t has the same fractions with x and y, but then instead of natural log of t, s over t, and instead of te to the s, e to the s. I'm going to say, if you got this far, great. This is not a final answer as far as I'm concerned. We're going to back substitute. Now, if you kind of take a look at the first fraction, the first expression here, the partial of z with respect to x. Nope. The partial of z with respect to s. Then we see we already have common denominators. And so it's just a matter of substituting in place of x, y, and x and y, and then expressing it as a single fraction where we have the definitions of x and y given at the beginning of the problem. For the partial of z with respect to t, I see that there's a fraction s over t in the first term and not in the second term. So it would make sense for us to go ahead and multiply by t over t to get common denominators. The substitution, and you can verify this if you would like, and of course you should if you haven't already done it, is that the partial of z with respect to s is 2s times the natural log of t, the quantity squared, plus 2t squared e to the 2s, divided by 1 plus the quantity of s squared times the natural log of t squared plus t squared e to the 2s, whole thing squared. Partial of z with respect to t is equal to 2s squared times the natural log of t plus 2t squared e to the 2s divided by t times 1 plus the quantity of s squared times the natural log of t squared plus t squared e to the 2s squared. That, cumbersome though it is our final answer.